Hello everyone, I'm Weimar and from University of Luxembourg. Today I will present our work, Commit-Aware Mutation Testing. Mutation testing has been shown to be one of the strongest software test criteria. We have one program and then randomly change the program to correct a lot of mutants. These mutants are different versions of the program, and then the tester executes test or do test generation for these mutants. And then we can get the mutation score to indicate the test quality. Although mutation testing has been widely studied, its formulation has remained unchanged since 1970s. The problem with this formulation is that it does not certify the recent software engineering practice. Modern software systems are changed frequently, typically in continuous integration environment. However, mutation testing is time costly. Our study tried to answer how to apply the powerful mutation testing in continuous integration. There are some challenges. First, mutation testing is resource intensive, and secondly, not all the mutants are useful to test the code change. It is not possible to use all the mutants in the continuous integration for each commit. Therefore, we need a new mutation testing formulation in which mutants can be found based on their relevance to the specific change in the software system. In this involving mutation testing approach, the set of mutants change with each new commit. Through these mutants, we can test commit change better. We propose use commit relevant mutants to test in continuous integration. We have the pre-commit program version, and then the developer submit one commit. We get the post-commit program version, and then we correct the mutant. The commit relevant mutants can capture the interaction between the commit code and the mutant we introduce. More precisely, the alt code affects the mutant behavior, and the mutant affects the alt code behavior at the same time. We also define a new mutation test metric, relevant mutation score, to see if the commit change is test-aware. Relevant mutation score is the ratio of killed relevant mutants among the total number of the relevant mutants. More details and examples are shared in our paper. The two tables summarize the data we use in our work. To study the commit relevant mutants, we use 81 commits for C program and Java program in total. From this table, we can see that we have a lot of test cases and mutants. We use the mutation tool MART and p-test to generate mutants. We also use simplification to generate more tests. More details about data collection process and the tools we use can be found in our paper. In our work, we have 4 research questions. The first one is mutant distribution, to see what is the proportion of relevant mutants. How many relevant mutants are from the commit change? The second research question is a metric relation, to see if it is good to use the traditional mutation score to replace relevant mutation score. What is their correlation? The third research question is test selection, to see if killing relevant mutants lead to the advantages over killing random mutants or mutants in the modification. However, it is important to know the actual test effectiveness of the relevant mutants, so that we have a research question 4 to see if killing relevant mutants results in the advantage to find the faults. The figure shows the C program result about research question 1. The majority of relevant mutants are outside of the commit modification, and the proportion of relevant mutants are very low among all the mutants. So that it means if only consider random mutants or the mutants in modification, we'll have a lot of noise of the bars compared with using the relevant mutants. The figure is about Java program. We can get the same conclusion. The figure shows C program result about research question 2. X-axis is the mutation score, Y-axis is the relevant mutation score. Each subfigure represents one commit. There is no pattern between mutation score and relevant mutation score. It means that it is necessary to compute relevant mutation score instead of mutation score to test commit change. The figure is about Java program. We can get the same conclusion. We also compute the conduct correlation between mutation score and relevant mutation score for research question 2. The correlation is weak. The two figures are about research question 3. The axis is the number of mutants we analyze. Y-axis is the relevant mutation score. The left figure is about C program. The right figure is about Java program. We use a few relevant mutants to do test selection. We can see that killing relevant mutants leads to the advantages to higher relevant mutation score and test the code behavior change. We also compute the test effect size, and more details can be found in our paper. The figure shows the result about research question 4. We select 27 mutants for each commit from cobunch. X-axis is the normalized percent of the number of mutants. Y-axis is the fault revision ratio. We can see that there is a big difference between relevant mutants, random mutants, and mutants in multiplication to find the fault. It shows that relevant mutants have the actual test effectiveness to find the fault in the program. We also compute the test effect size, and more details can be found in our paper. From our work, we can draw some main conclusions. You can find more details in our paper. The first conclusion is that many relevant mutants are outside of the code modification. Only considering the mutants in modification or random mutants will have large bars and noise. The second conclusion is that the traditional mutation score has a weak correlation with the relevant mutation score. Mutation score cannot indicate the relevant mutation score. The third conclusion is that using the relevant mutants to select the test leads to the advantages to test the commit code change. The last conclusion is that the relevant mutants have the actual test effectiveness to find more results. We also build a website, and we put more supplement materials in the website, and you can find the link and more details in our paper. Thanks.